Hi, this is Mrs. Verbal. This is part 3 of covalent bonding. So in the first two videos, we talked about what is a covalent bond, how do we identify it. We also looked at polar covalent bonds and how you can determine whether or not something is polar. And we also looked at the different types of bonds and how to identify the various types. Now we're going to start looking at the geometry of a molecule, and we're going to use the valence shell electron pair repulsion idea to help us determine what is the structure of the molecule. So the first compound that we want to look at is ethene. Ethene is actually naturally found with ripening of fruit. So if you have bananas in your kitchen and you put them in a brown paper bag, eventually the gas would accumulate, and that would help to turn the bananas from green to yellow. Now notice with ethene, we're looking at multiple bonds. So we have a total of 5 sigma bonds. So there's one between the two carbon atoms, and then there's 4 sigma bonds between carbon and hydrogen. Notice that there's one sigma bond and its location is above or below the carbon-carbon bond. Here we go. Now there's something which we call resonance. If you do the water goblet trick where you have a crystal glass and you fill it a certain height of water and you run your finger around the edges, you can actually get some resonance with sound. Well, there's something a little bit different with chemical resonance. You can have 2 or more dot diagrams, and the interesting thing is that neither one is considered incorrect. But what happens is electrons can move around with covalent bonding, and that's essentially what happens with resonance. And I'll show you a picture of this here. So we have NO3-. This is actually a polyatomic ion, and notice it has a -1 charge, okay? So what happens is the way the electrons are, they float or they travel between the 3 oxygen atoms. So notice we have a double bond here, and then it shifts over here, and then eventually it comes down here. Each structure is correct. It's just that there's no preferential treatment between the different oxygens. If you were to stop and freeze these structures in one time, you know, a third of them will have a double bond here, a third of them will have a double bond here, and a third of them will have a double bond there. Okay. Yeah. I mean, this is just a way to let us know that sometimes we take not artistic license, but we're just showing that the electrons are going to partially reside between each oxygen. And this double bond just shows you that because of resonance, we're going to have multiple bonds, and they're going to be shared equally between the 3 oxygens. So up to this point, we've talked about covalent bonds, polar covalent bonds. We've talked about valence shell electron pair repulsion. We just started talking about geometry, and now I want to talk about nomenclature with you. Now, before I do, I want to talk about properties of covalent bonds. Now, here we have non-electrolytes. So remember, when we talked about electrolytes, we were looking at ionic bonding. Now we're talking about non-electrolytes. So these are solutions that do not conduct any kind of current. If you took sugar and you put it in water and you tried to energize a light bulb, and hopefully I've shown you that in class, you're going to find not much is going on there, and that's because they're neutral. So we call these molecules neutral, and hence the term non-electrolytes. Now, we're treating the non-electrolytes a little bit different than ionic compounds. We call them molecular formulas, and we also look at their masses as molecular masses. Most non-electrolytes are a combination of metalloids or nonmetals, and the whole crux of it is you're going to look for nonmetals because that typically forms a non-electrolyte. Okay, some of the properties. A good chunk of these are soluble in water, but there's some that are not. They may require a different type of solvent, and we'll talk about that eventually. If they are soluble by water, they will undergo what we call dissociation. So just like with ionic compounds, we looked at a separation of ions. So same things going on. Now, there are acids that are an exception to the rule. And eventually we'll talk about acids. Okay, here we go. Compared to ionic compounds, non-electrolytes tend to have low melting boiling points. So they don't have the strong bonds that typically are found in ionic compounds. They are not as durable as ionic compounds. You may notice that they're more brittle because of that. But the interesting thing is with non-electrolytes, you can have all different phases. So you don't necessarily have just solids at room temperature. You could have liquids at room temperature. You could have gases at room temperature.